those are called, previous examples are those what we call the limits at infinity, whether it's going to the left or to the right. Now we have a what we call infinite limits. So infinite limit is this one. When you go to something finite, A is finite, it gets closer to A, but it gives you either plus or minus infinity. So it's large, but depending on the whether it's going to positive direction or negative directions. This is large, either positive or negative directions. Okay. So how you interpret that? So this when x equals a, oh sorry, so what we call f gets close to infinity. What is close to infinity? Because infinity is always far, so you never get close to something far. As x gets closer to a. So gets close to this just saying that gets larger and larger. Okay, so it gets larger and larger. So what does it mean? So we describe this as f is getting larger than m. Okay, so in our notation, m is large, epsilon is small. So this one gets closer. Okay, so what is this one here? So this is what we call delta. So in other words, this is how we define this limit. Limit x going to a, for example, say the plus 1, meaning that for every m positive, you can find delta positive, this delta, so that f of x larger than m for x minus 1. Okay. Or type of infinity limit. Okay. It can be replaced by one-sided plus or minus infinity, or you can also one-sided minus infinity, or this one also one-sided from left. Okay, so those are we call the infinite limits, infinity limits, or infinite limits. Okay, so for example here, okay, x goes to 0 positive of 1 over x is plus infinity. So how we see this one? Okay. All right. So that's our scratch here. So we would like to have just 1 over x, okay, larger than m. Okay, so this is our uh, the objective. So we would like to see how small x could be. Okay, so just take reciprocate. Okay, so x 1 over m, but the inequality sign reversed. So that's how you get this. Okay, so in this case from the right, so let's just keep x. All right, so this is okay. So uh, let m be positive number. So we choose delta to be this one, 1 over m. Then if x, oh, not 0, you cannot divide by 0, m by delta, say. Then what happens to this one? So 1 over x is smaller than 1 over delta, which is 1 over m, which is, okay. So then this is what you have. This definition is satisfied by this small computation, these observations. Okay, so that's meaning that x is going to uh, is plus infinity. Okay. On the other hand, you can check that this limit. But you get infinity also, but sorry. Okay. So the pictures of 1 over x, now we get a complete picture of 1 over x. There. There. Okay. So we call this is the horizontal asymptote. This is what we call the vertical asymptote. Okay. So the line x equals a is horizontal, sorry, vertical. A vertical asymptote. Or y equal f of x if any of following occurs. 1, x going to a from the going directions is plus or minus infinity. Going from the left, sorry, from the right is either plus infinity or minus infinity, or going to a from approaching a from the left is either or negative. Okay, so this is the case. Okay, or you may have also square, same thing. So y-axis is also a, I call a vertical asymptote. Okay. All right. Questions? All right. Let's use some more examples. Okay, that's all right. And about asymptotes, there's another asymptotes that I would like to recall that you might have heard about slant asymptote. Slant asymptote is an asymptote, but it is not a vertical or nor nor neither vertical nor horizontal. Vertical or horizontal. So that means asymptote maybe looks like this one. So the picture looks like that. Okay. So going far to the, for example, this one is y mx plus b. Okay. So this is the situations that going far to the right, the graph of f it looks like the graph of this line. Okay. So the situation tells you that far to the right, f of x tends to the line x plus b. Okay. So what does it mean? Of course, you cannot say far to the right. Far to the right is this. Okay, tends to the line. So this is the limit. But the thing is, well, you cannot have this one. Here, if you take compute the limit, there's no x anymore. Just give you a number. Right? Here we have x still x. X is going to infinity. How this possibly do? Okay. So what happened is that here, y equal fx plus b is slant asymptote if, of course, going far to the right, but you're looking at minus x plus b. There is 0. Okay, so that's what you get. But how to find the slant asymptote? So what you have here is that if we have irrational functions, This is polynomial over polynomial. Okay, polynomial. So you would have at the end close to mx plus b, for example. Okay. You should have, well, the thing is, say p1 is power 10, right? P2 is power 5. So if you divide P1 by P2, you get x power of 5. So you cannot have this one, right? So the only thing possible to have mx plus b is that, say, for example, P is power 2, P2 is power 1, P1 power 5, P2 power 4, right? So, so power of order of P1 minus order of P2 must be 1. So that's the only thing possible. Okay, so let's find this out. All right. So slant asymptote only occurs when P1x, where P1, P2 are polynomial, and order of polynomial 1 is the same as order of polynomial 2 plus 1. So simple. So when you have this, you don't have slant asymptote. All right, example. Find slant asymptote. It exists. So 2 problems. Okay. Okay. Y equals x. Okay. All right, so let's see here. Numerator is power 3. This is power 3. All right. So you have asymptotes, but it is not slant asymptotes. You see, this has a horizontal asymptote. Y equals 1. 1 because this has the same power. So we divide it by the x cubed, both numerator and denominators. And then you get just this coefficient 1 by this coefficient. Okay, so 1 over 1, so that's going. Okay. This one power 3, this one power 2. So this is exactly, you have slant asymptote. We need to find this one. When you have this, you have a cube on numerators and just linear, power 1 denominator. So the difference is 2. When you divide this out, this you get x squared. So you don't have slant asymptote. You may say the difference, not difference, the ratio should be x squared, right? X squared is the parabola. So is there anything like parabolic asymptotes? Well, if you'd like to define so, then you may, but what we have slant asymptote is a line. So how to find this one? Let's compute this one by long division. By long division, this one. Okay, so divide this out. Cube divided by square, so you have x. Multiply this out. Plus x. There we go. Subtract, so you get cube will cancel, so you get x squared minus x plus 5. When you divide by this, you can no longer divide by x squared plus 1. Okay, so what we have is that x cubed plus 5 divided by is just x. Okay, we add over, oh sorry, we haven't finished yet. You can still divide because this is square, this is square, so you get 1. Plus 1, and you still subtract. This square disappear. What we have is x minus 6. Oh, sorry, not minus 6. This is 5, subtract 1, so this 4. Okay, so the conclusion is that x cubed plus x squared plus 5 divides by is x plus 1, right? Over, also plus minus x plus 4 divides by x squared plus 1. Okay, so when we compute this one, limit x going to, let's see, going far to the left, far to the right, plus 1, right? It's like same as, not this one, and subtract. All right, this is going to be our mx plus b. So you, there. Okay, you move this to the left hand side. So what's left is there. Okay. So when you have this one, but well, you divide by a square here. Okay, so you get after this goes to 0, this goes to 0, this goes to 1. So what we have is just this goes to, sorry, yeah, this goes to 0, this goes to 1. That's it. All right, so that's this shows you that y equals x plus 1 is the slant asymptote. Okay, so looking for slant is not a calculus at all, just algebra using long division. All right. Okay, so then let's finish this part up by continuity. All right, so let's say what do you continue to? The function f is said to be continuous at x equals a if these situations equals f of a. So what is this? All right, so this is value of f, value at a, at a, at this one is value of f near a. All right. So this is the what we call earlier the easy case when computing limit is nothing but the substituting the a to the f. Right. So this is what we call continuous. And if you recall some of the illustration that I told you in the beginning of the course, value of a is like if you're observing say a person, right? But observing indirectly, meaning you have to find out about the person from his or her friends, circle of friends. Okay, so you interview his or her friends, keep getting closer and closer, and from the observations, from the interviews, you conclude something about that person. It's called prediction, right? So f of a is just the about the person itself. The limit is the approximations. So when approximations match up with the real one, then it is called continuous. Okay. So another example is that if you're in, say, for sure, this is not on online situations. You're in a classroom. You're not in the class. Sorry, you're not in a classroom except your friends, right? And all your friends in the classroom have white shirts. All your friends have white shirts. And I was just thinking over what if you were in the class? What color of shirts you would wear? But since all your friends here wear white, then you could assume that you also have to wear white. So from your friend, you can make predictions what f should be at a. But then the value f at a is unrelated to this fact. But if they are the same, that's what we call continuous. Okay. So implicitly, it assumes one thing, that the limit exists okay. Uh, f is defined at a, and the third, they are the same. Okay, so if limit doesn't exist, then we say it's not continuous. But a is part of the domain. So in this case, a is in the domain. Okay, so then that's what we call continuous. All right, so what's the situation we have here? Okay, so we have this is 3, this is 1, for example. This picture. In these situations, we have, say, limit 1 from the left is 1. Same thing as from the right. So they exist. But the value f1 is 3, and they are not the same. So we conclude this f is not continuous. F x equals 1. Okay. And you have also in this case, you see that sorry, should be red. In this case, you see that the even limit doesn't exist. Doesn't exist. Why? Because the one-sided don't match. Don't match. Okay. So that's the limit. And what else? Continuity. So there's okay. Okay. So what are the continuous functions? Okay, so that's the situations. Oh, sorry. Question should be what class of functions, what classes are continuous? Well, we know that if you have a polynomial, P is polynomial, then we know that the limit exists always, and it's the easy case. Okay. That means P is continuous. So P is continuous at any A. Okay. So if F is rational, rational functions also P1, this is P2 over X. Okay. So as long as this one, so this is the, no, this is also easy case, as long as A is in the domain of F. Okay. So what we call is that F is continuous at any A inside the domain. Okay, okay, for example, uh, let's see, okay, here. 1/8, right? As long as A is not 0. So we can say that fx1/x, this is 1/x, is continuous when x is not 0. But what about 0? The thing is, sorry, I should say this, is at A is not 0. What about A is a 0? Then this is not in the domain 1/x. So at A is irrelevant to say this continuous or discontinuous. Okay, so at A, uh, continuity is irrelevant. Okay? Why? Because this is irrelevant because this is not in the domain. Okay. So this is what we have so far. Okay, this continuity. One more example. So you have what are continuous functions? Functions. So we have polynomials. Rational functions. You have trig functions. Sorry, rational functions. Inside the domain. Okay. Also, trig functions inside the domain also. Okay. What else? Root functions. Roots, absolute value. Those are the continuous functions. Okay. And what else? Well, okay. Sum or difference of continuous functions. Or the product or divisions ratio, say. Can define later. Hello, hello. Can you hear me?
Yes, sir.
Yes, sir, it's clear.
All right. The the cable's pulled off. So all right. Uh, Ratio functions. All right. So those are the continuous functions. What else? Or composition of continuous functions. Also. It's also continuous. All right. And okay. And okay, I think I should stop here because we'll take some time to give examples of the problems with this. So we'll continue that next week. So with the end of this chapter, start with the new one next week. All right. So the quiz won't include the continuity, but we'll stop at the infinite limits and limit as infinity. All right, questions?
No questions.
Sure. All right, if no questions, then the attendance is open until 9:30. See how to get it.